Hey Kim, today we're going to be reviewing a little bit about acids and bases, specifically the properties of acids and bases, and then talking about pH and pOH. So acids are actually a lot more common than you might want to think. Most of the foods that we eat are actually acidic. So all the citrus fruits, coffee, soda, vinegar, all of that is acidic. It's also present in our stomach to help us aid in digestion. So a lot of people, when they think of acids, they think of something that's dangerous, when in reality, a lot of the acid that we encounter is actually very safe. We even eat it and consume it. So it's not that dangerous. That being said, acids in the laboratory, of course, are typically more concentrated and then are dangerous. So you don't want to get acid in your eye or on your hands or anything, which is why we practice safe lab practices. And basically, acids and bases are distinct categories that are based on their properties, specifically in aqueous solutions. So here are 5 common properties of acids. The first is that they're electrolytes. They ionize in water, and strong acids are those that ionize completely, typically into H+ and then an anion. And others are weaker, so they don't really completely ionize. So those types of acids, if we were to show their ionization in a chemical equation, we would use a double arrow to show that it goes both forward and reverse, meaning it's not very strong. Versus strong acids, we just use a single forward arrow to show that reaction. Acids have a sour taste, so again, if you think of like citrus, vinegar, typically they have a sour flavor. But of course, we do not taste acids in the lab. Acids do change the color of acid-base indicators, which is why indicators are so helpful because they indicate whether something is an acid or a base. The most common indicators that we will encounter are litmus, typically litmus paper, which is just a strip of paper that you dip into the solution, and phenolphthalein. Blue litmus paper would turn red in the presence of an acid, so red litmus means acid, and then phenolphthalein is going to be colorless in an acid. They also react with metals, typically active metals, so very reactive metals, to produce hydrogen gas, which usually we see this by bubbling. So we put acid on a metal, usually we'll see bubbling occur. Metals that react with acid are located above hydrogen in a reactivity series or an activity series. So you don't have to necessarily memorize what metals are reactive and will react with acid. Usually you'll be given an activity series to show this, and the reaction that takes place is a single replacement reaction. Acids also react with bases to produce water and a salt compound. This is called a neutralization reaction because the pH of the solution is neutral. Bases is typically in stuff that we do not usually eat or drink. While there are some basic food products, like eggs are typically a little bit basic, most of the stronger bases are like cleaning products and soap. So a lot of people think that acids are dangerous. That must mean that bases are safe, when really bases are the stuff that we have that we lock up from kids in cabinets because it's very dangerous if you consume them. Things like bleach and laundry detergent shouldn't be consumed. They're very basic. There are some basic substances that can be consumed. Some are foods, but a lot is actually medications. So for example, antacid tablets like Tums. If you were in my regular chem around Thanksgiving, I do a neutralization reaction demonstration using Tums and milk of magnesia, which is another medication that is used to treat heartburn. And it basically shows how it changes the pH of your stomach. So typically if you eat too much, your stomach starts producing a lot of HCl or stomach acid, which can in turn lead to heartburn. And acids try to neutralize your stomach a little bit, raise the pH, lower the amount of acid that is in your stomach by a neutralization reaction. So the properties of bases relate to that of acids. Some are opposite and some are rather similar. So, like acids, they do form electrolytes in a solution. Bases can be strong or weak, just like acids are strong or weak. Instead of having a sour taste, bases have a bitter taste, but again, I don't really recommend that you taste bases, although there are some more basic foods. So anything that tastes bitter is typically a little bit basic. Soaps are usually slippery to the touch, so bases are also typically slippery. So like if you think of laundry detergent, how it feels if you get laundry detergent on your fingers, it's pretty slippery. But again, in lab, we just don't dip our hand in solution and feel if it's slippery or not. Bases also change the color of acid-base indicators. Litmus will turn blue in the presence of a base, so blue base, red acid. And then the phenolphthalein turns pink, whereas in an acid it's clear. So this phenolphthalein is typically used in what we call a titration experiment, where we start with something with the acid indicator in it that is typically clear, and then we titrate a base into it and then stop the titration when it turns pink. And it's just something that we can use to measure pH. But I will talk about titrations more later. Bases don't really react with metals in the same way that acids do. And again, bases and acids react together to produce a salt, which is a metal, a nonmetal, and an ionic compound, and water. So pH is something that we use to describe the acidity of a solution, and it's on a scale from 0 to 14 or 1 to 14. Anything low on the scale has high acidity. Anything high on the scale has more basic qualities. So a lot of people think high pH means really acidic. Again, I think it comes with the misconception that acids are really dangerous and reactive and things like that. But high pH is actually basic. pH actually means power of the hydrogen ion. So pH is a measure of acidity, which can be thought of as the concentration of what we are going to talk more about in the next presentation of H+, which is a proton or a hydrogen ion. So H+ is a really good indicator of acids. So we're measuring that concentration of H+. The thing is, in acids, this concentration can be pretty small. So for example, in water, which is neutral, the concentration of H+ is 1 times 10 to the negative 7. In something very acidic, it would be 1 times 10 to the negative 1. So still like a relatively small amount. So we use the logarithmic scale to actually calculate this. Okay, so to calculate the pH of something, it can be from 0 to 14. It doesn't have to be a whole number, it can have decimals. You take the negative log in your calculator of the concentration of H+. So again, in water, a neutral solution, 1 times 10 to the negative 7, if we take the negative log of that, we get a pH of 7. And you can type that into your calculator and hopefully you see that. They're not always nice, neat 1 times 10 to an exponent. So clearly you can see that the negative of the exponent is the pH in this example. You can have like 2.15 times 10 to the negative 6 or something like that. But you can still plug that concentration in to this equation here and find the pH. This capital M, again, is molarity, so moles per liter of solution. A solution of pH of 6 doesn't sound that more acidic than a pH of 7, but in reality, since we're talking about a logarithmic scale here, it has at least 10 times more H+ ions in the solution than one with a pH of 7. A solution with a pH of 5 has 100 times more H+ in the solution compared to a solution with a pH of 7. So it is logarithmic. It's not just a change of 1. It's a change of 10 times for every 1 because of the logarithmic scale. To solve for the concentration of H given a pH, you're basically doing the opposite of a log or negative log, which is taking 10 to the power of the negative pH. So this is the equation you would use if you were interested in the concentration of H+ in a solution and you were given pH of the solution. So a lot of, if you've ever tested like pools or your fish tank for pH, a lot of times it will give you a number based on a color. So you could do 10 to that negative pH and find the concentration of H+ in the solution. So these are kind of the two important equations here. We can also consider POH, which is it goes together with pH, but instead of describing the concentration of H+, it's describing the concentration of OH-, which is typically associated with bases. So POH is the power of the hydroxide ion, which is OH-. To calculate POH, you would take the negative log of OH-, of the concentration of OH-, which is again in molarity. I forgot to mention as well, these square brackets typically just mean concentration. So for concentration, we don't use typical rounded parentheses, we use these square brackets. If you were to add together your POH of a solution and pH of a solution, it would equal 14. So if you're given the pH of a solution and you want to find POH, all that you have to do is subtract 14 minus the pH you're given to find POH. And vice versa. If you want to find pH and you're given the POH, then you take 14 minus the POH of a solution. So typically, scientists use pH. We don't really use POH often, but for example, if they give you the concentration of OH-, it can be easier to find the POH. So then we could find the POH and then solve for pH that way, rather than trying to figure out what the concentration of H+ is if they don't give it to you. So that's why we talk about POH. It's really mostly useful for finding pH if you don't have enough information to find pH. And this is a scale here, again, that just shows your pH scale, and it also compares it to the colors of the litmus paper. So again, acids make litmus paper red, bases make it blue. This shows you the concentration of H+, and it also gives you some nice examples, which is nice. So coffee, tomato juice, orange juice, pop, vinegar, lemon juice, stomach acid, those are all acidic things. Milk is slightly acidic, pure water is neutral, blood is a little bit basic, eggs are pretty basic. I would say that Tums would be located somewhere near eggs. Tums aren't really that basic. Milk with magnesia is a lot more basic than Tums are. And again, you have in your higher pH zone, you have the dangerous things like detergent, soap, ammonia, household bleach, sodium hydroxide, things you don't really want to consume. Okay? So in the next presentation, we'll be going over different definitions of acids and bases, and let me know if you have any questions.